So taking a look at ACI multicast fabric forwarding, we talked about the fact that we might have multiple tenants and they might be using the same IP address range, VLAN or VXLAN range, MAC addresses, but they also might be using the same multicast group IDs. Okay? And so we need to have an overlay multicast group that can be used within the ACI fabric that's unique, regardless of whether two different clients happen to have, let's say Cisco Unified Communication Manager, music on hold, running at 239.1.1.1. Okay? So we would still be able to serve them because those two separate tenants or five separate tenants running those same multicast music or just multicast groups would get a new IP overlay multicast group called the GIPO. Okay, and this was one of the fields, or really one of the values that you set or left by default when you first did the fabric turn-up, the fabric discovery. It was one of those first wizard questions. Okay, and we're going to have 16 trees beginning at counting at 0, so 0 through 15. And if we have 2 spines, we would have 8 trees on one, 8 trees on the other. If we have 4, they each have 4 trees. But for up to 16 different groups, and really we could have hundreds of groups, we're going to divide those equally up into 16 separate F tags, determining the root. Now in Fabric Path you had to manually configure the root to be the spines. That's all done automatically in ACI. A lot of things are done automatically. Okay? So we will go ahead and encapsulate. Let's say we get a multicast packet in on this vSwitch 1. When it gets to the leaf, if it's destined for another device on the same leaf, it will be switched locally. However, if it were going to another leaf switch, this is where we would get the new overlay group IP, and this would then get mapped to a particular F tag, and it would get sent to one of the spines, specifically the spine. In this case, let's say the F tag is F tag 11. It would get sent to spine 4, and then if the traffic were going out to multiple leafs, it would get redistributed back out to all the leafs, but with this being the root for that multicast tree. It's going to be replicated, and then when it gets to the leaf, that group IP as well as the VXLAN will be removed, and the traffic will go down to the receiver. So endpoint learning and lookup. We've actually already talked a lot about this. We're going to talk about a few more things. So for tenants, endpoints get learned with data plane traffic. So we learn the location of a particular VM or bare metal host, as well as its identity, mapping at the leaf. Of course, the spine maintains a copy of all this information of location and identity via the COOP protocol. So any DHCP forwarding can be used, ARP, GARP, and RARP. Any virtual machine manager, which is VMM. Okay, so let's say vCenter we see here. Okay, when we actually have a VM that is mapped to a particular port group on a VDS, a VMware distributed switch, or virtual distributed switch technically, that information is of course sent to vCenter, and vCenter sends the information to APIC because APIC has basically done a SOAP API request for a subscription to this. And then the APIC can match that up with the data management engine on the leaf switch, and it can learn of location in that direction. We're going to talk a lot more about VMM a little bit later, so we'll save that for another module. So we've already talked about how traffic ingresses to a vSwitch, how the leaf switch programs or actually learns and adds this to the local station table. This optionally can be pre-programmed or kind of statically programmed by the APIC if we need to or desire to. This information is forwarded to the spine through the COOP protocol. The database sharding occurs so that every spine has a consistent copy of the proxy table. And then the egress leaf is going to learn of that internal IP MAC, and it's going to cache the source VTEP address in its global station table. Then the leaf is going to forward the frame to the switch and be transmitted to the VM. So we also talked about policy identification and enforcement, specifically that the source group, or the source EPG or endpoint group, is going to be used as a tag or a label, specifically the class ID. And whenever a VM or machine, a host, attaches to our fabric, we'll learn the source group, tag the VXLAN header with its class ID. And then policy can be enforced at the ingress or egress, the source or destination, based on if the source knows about not only the source group but also the destination EPG. If it does, it will apply policy at the source. So here's an example. So the EPG is derived based on classification. So it could be based on the VMware port group, the physical port that we see traffic on the Leaf server, if maybe it's a bare metal machine or a router, the IP address, the VLAN, it could be the MAC address of the VM using VM attributes based or micro EPGs, as we've already alluded to. It could be the VLAN name, the VM name, the virtual machine name. Could be any number of 10 attributes there if we're doing micro EPG. At this point, the vSwitch is going to encapsulate it, and if it knew about not only the source but also the destination group, then it will populate the SP flag with 1 and the source group with the class ID. At this point, if the source policy bit was set to 0, the egress leaf is going to set the DP bit when it enforces policy, and then it would be forwarded onto the VM. Now, in the web user interface, if you navigate to the EPG Operational tab, which we'll be taking a look at in detail in the demonstration, and we verify that the endpoint is learned. So this is when we click on the EPG, and then over in the right work pane or properties pane, we click on the Operational tab. Okay? From there, we can see whether the VM was learned. And we can also see what path or port. So in this case, a bare metal machine with a particular MAC address, no IP learning was done, okay, was seen on Leaf node 17, port ETH 1/5, and it was known because of either the port or possibly because of the VLAN. And of course, this is something that we would have configured on the EPG. How did you know about this particular traffic? Was it based on the port? Or if this is a trunk, we could have multiple different EPGs learning about traffic on this particular Leaf 17 port 1.5, but the VLAN IDs are different, and that's how we classify the traffic into different EPGs. If this is a virtual machine manager, we might learn of the ESXi or any sort of KVM or Microsoft Hyper-V, the hypervisor. This is the hosting server. We would even learn the endpoint name. We'll talk about these two different types of learning. If we're in a VMM domain, then it's important that both learned and VMM are there. Otherwise, we won't have traffic. And then how did we learn about it? Well, we learned about it through a particular vCenter, actually through vCenter, in this case, this particular vCenter name. Okay? Might be Microsoft System Center, might be OpenStack. And then what was the IP address of the in this case, what is the IP address of the node or the node port that we learned it on, and possibly the VLAN encapsulation. So also, we can take a look at what the proxy or the spine proxy tables hold. So really what the entire fabric sees, rather than just a particular leaf or a particular EPG. So we can go up to the Fabric tab, up to Pod 1, Operational tab, as we can see here, and take a look at the global endpoints. And we can see all the mappings, the VLAN encapsulations or VXLAN encapsulations, how they were learned, the IP addresses if they're there, and the MAC addresses. We can also, as we talked about earlier, filter for a particular IP or MAC to make it very easy to see where that device lives. So finally, we come to the end of this module, and we're going to talk about fabric innovations. So some of our fabric innovations are the ability, and we've alluded to this a lot, to eliminate the need for ARP and for unknown unicast flooding. So the idea is that if we have learned not only the source as well as the destination, not only MAC address, but really the destination IP address, then we have the ability, or the leaf switch in ACI has the ability, to do a lookup in the data payload, specifically for an ARP packet, and take a look at the destination IP address in that ARP broadcast packet. So from there, it can say, I know about that destination IP address, and so we don't need to flood that traffic everywhere or broadcast it. We can simply unicast it to the IP address that we know of. And if Leaf 2 doesn't know of the destination IP, it can unicast punt it to a spine proxy table, which will do the lookup and know it can punt it directly or forward it on directly to the unicast VTEP of the leaf that owns that VM, at least currently, okay, until it vMotions. So the result of this is no flooding of ARP traffic. Now, if you untick that box for unicast routing, then you also have to turn on unknown unicast flooding, as well as turn on ARP flooding. Okay, so this would be important. Another thing to consider is that if you're linking a particular VXLAN bridge domain to an external legacy non-VXLAN, right, regular VLAN switched environment, then you're also going to have to turn on unknown unicast flooding and turn on ARP flooding, because the legacy environment doesn't know or have those fabric innovations, and so the leaf or possibly the spine proxy would never forward that traffic on because it hadn't learned all that flooding information. So it is important when we're connecting to external layer 2 for a particular VXLAN bridge domain, or if we turn off unicast routing, to go ahead and disable this innovation of the reduction or elimination of ARP flooding. Another thing deals with gratuitous ARP and device movement, right? So if a VM moves and the GARP or RARP occurs, the leaf ASIC is going to forward that GARP to the leaf where the VM originally was attached, but it doesn't need to flood it everywhere. Again, if we learned IP addresses. And that way, the leaf where it was originally attached can install the bounce entry, but we're not flooding traffic, we're simply unicasting that traffic. Now, if we did not have unicast routing on, then it would need to be flooded. Okay? So the flooding still can occur to mimic and utilize legacy environments, but if we're learning IP addresses, we don't need to do that, and then the bounce entry can occur. Now, one of the other fabric innovations that I've been alluding to this whole time is this idea of TCP Microflowlet switching, which was actually something that Kandula and his associates back in 11 years now, 2004, came up with the concept, essentially, that if the gap between, well, actually, let's take a step back. TCP is very bursty in nature, right? So because TCP is bursty in nature, we'll see bursts of traffic. And there is a delay, even if it's a small delay, much smaller than, maybe even milliseconds, but if there's a delay between the bursts of traffic, whether it's the same delay or difference in delay, doesn't really matter, okay, whether we have jitter in our delay, the leaf can see the delay between, or the gap between the first burst of packets and the next burst of packets, and so we'll call this burst D1 and D2. Okay? So let's say we have host 2 sending traffic to host 1. Actually, sorry, the other way around. So we just have the animations out of order and it's already received the packets before it ever sent them. It's magic. No, sorry. Got to fix that animation. At any rate, if H1, host 1, goes ahead and sends its first D1 burst of packets, and now, all of a sudden, the second burst of packets is coming in. It's a part of the same TCP flow, but if the leaf switch can detect that the delay between those two is basically greater than one of the other links' latency, then it can go ahead and send that traffic out another link and ensure that it's going to get received by the egress leaf 3 in this case, by the egress VTEP, still in order. Now this doesn't incur any additional latency. This is not using buffering. It's not storing the traffic and then forwarding it. It's just simply saying, I have visibility not only, and if we think about this, it not only has to have visibility, let's say leaf 1, of a particular link, but really of a particular path, right? So I could go to, let's say, I could go out link 1 to get to leaf 3, but I could also go out link 2 to get to leaf 3, go out link 3 to get to leaf 3, or go out link 4 to spine 4 to get to leaf 3. So, but it's also possible, if you think about it, that I might have multiple links. So I might have multiple links from leaf 1 to spine 4, and it's also possible that spine 4 to leaf 3 might have multiple links. So it's not only per link, but it's actually per path. So the complete path from leaf 1 through a particular link, through another particular link to the destination. So how does it do this? Well, this is what we talked about at the beginning, or pseudo-beginning of this module. We looked at the VXLAN header, and we looked to see if LB was set, the load balancing, and the DRE, or the DRE bit. Okay? So the discount rate estimator. And remember how I said this was somewhat analogous to the mobile driving application Waze, right? So in Waze, essentially what you do, if you're not familiar with it, is everyone turns on their mobile phone, well, whoever is using Waze, they turn on their mobile phone, they fire up the app, of course, and you begin reporting back to a centralized server, kind of, I don't know, Big Brother or HAL 9000, if you will, whatever. You begin reporting back to the centralized server all of the information about your location. And you have to, of course, agree to this before you can use the app. Okay, so it's constantly reporting back your location and your speed. So as you begin slowing down, Waze says, hey, we detected a slowdown. Are you in traffic? And it actually reports that information back. And then you can also tag it and say, yep, we're in traffic. It's either heavy, moderate, or a light kind of traffic buildup on this particular route. Now maybe you reroute and you change somewhere else. But the idea is that Waze can update your route based on all the real-time analytics, all the metrics, right? All of these atomic counters, if you will, back to a centralized server, and the centralized server can make forwarding decisions and reroute you, well, at least reroute your map application. You don't really have to comply. Remember, this is a declarative policy, not an imperative. So it doesn't well, if you're driving a Google car, maybe it steers it for you, since Google now owns Waze. At any rate, I digress. Stay with me here for a moment. Okay, so it's a declarative model. So it declares to your app, hey, we're rerouting you to a new location. And maybe it's having you get off the freeway and take surface streets. Funny story about Waze. My wife does not like to deviate from anything she knows. So she was using a regular navigation, and we were on a 10-hour trip with our kids to see my in-laws, her parents, right? And it's 11 p.m. at night, or 2300, and we are driving on State Route 10, and all of a sudden Waze said, and it's a straight route, like you don't get off until you get to her place, right? From LA all the way to New Mexico. So it is, all of a sudden it says, get off the route. Get off the freeway, get off the motorway, and take some surface streets. And it takes her, and she's like, this is wrong. It has no idea what it's doing. I'm doing 65 miles an hour. It's smooth sailing. It has no idea what it's talking about. I said, you should listen. She said, it has no idea. I said, you should listen. So finally I get her to comply, and she pulls off the route. She goes onto a side street, but we're actually in the middle of like a kind of a just nothing, right? Wilderness. So all of a sudden it takes her directly way away from the freeway. and all of a sudden she's now on a gravel road and in cornfields, and she is livid. She is angry. She is like, I told you we should not have listened to this stupid thing. So I said, okay, but we are where we are now, so just let's keep following it. And she's getting worried it's taking us and getting us lost. Finally, it begins taking us back to the freeway, and where it brings us back to the freeway, we're now driving parallel on a service road, parallel to the freeway, and all of a sudden we can see that there is a 3 semi-truck pileup, and the entire freeway is closed. And she looks over at me and she says, I'll never doubt you again. And I said, thank you. At any rate, little humor to kind of give you an idea of, can you trust TCP microflow switching with ACI? And this idea that our atomic counters built into our ALE and ASE ASICs actually provide full visibility back to the APIC controller, and the APIC controller updates all the leaf and spine switches with real-time information. And by the way, NTP is critical to this. In fact, it just won't even turn on otherwise. And trust that we see one of those other fields in the end of that header was the metric for the load utilization. It's a 8-bit value, so really a load factor of 1 up to 255. So maybe if a particular link or a particular path is halfway loaded with traffic, 40 gig up to the spine and then down, so 40 gig throughput for the whole path, it might, and 20 gig is utilized, maybe it would be a value of, let's say, 128 over 255, okay? So it's going to give an indication of the load and the latency for each path and even each link. And it's by this that we can detect, or the source, Ingress leaf, can detect the gap between our D1 burst of frames within a single flow and our D2 burst of frames, not flames, within a single flow. And I've seen this, I've turned it on using the same day that I had Ixia out doing testing, 20 gig in 2 separate ports ingressing from one leaf, sending over to another leaf, and 20 gig from 2 separate ports ingressing from the second leaf, sending over to the first leaf, with multiple senders and receivers, so lots of different flows being generated. And we turned it on, and we immediately saw what was a very unequal distribution of load. Everything was still forwarding at line rate, but our first link, we only had 2 spines and 2 leaves in this particular test. Okay? Everything was forwarding from one leaf to one spine. Well, not everything, but I would say the majority of traffic. Actually, it was closer to like 86% was forwarding over one link, and the other, 14%, I suppose, was forwarding over the second link to the second spine. Now, everything was still forwarding at line rate, so it wasn't a problem. However, if that first link got fully utilized, there's nothing that's going to tell the additional traffic to reroute over another link in a traditional network or even in ACI unless we turn this on. Why? Because our static hash buckets have already been set up. So we could possibly overutilize a single link and then go into a situation where we're oversubscribed on a particular link. We turned on TCP Microflow switching. Immediately, we saw things jump to 46-54% load balancing between the 2 links. Not a single dropped frame. And Ixia looks at both the source and the destination, because it's hardware source and destination, traffic monitoring or traffic generation and reception, receiving. And there was not one out of order packet. We can or out of order frame. And we can turn this on in 2 modes, aggressive or conservative. We tried both. So conservative, it looks for a longer gap between bursts. Aggressive, it looks for a shorter gap and switches it there, or switches it to another path faster. Neither one had any out of order frames. So finally, something else, and this I think is the last slide. We have something else called dynamic flow prioritization. Now this is mutually exclusive from the last option, flowlet switching. You cannot turn both on. In fact, when you try to turn both on, it'll give you an error and say it's not supported. But we can take our pick. So dynamic flow prioritization basically tries to deal with the issue of elephant flows. So if we were using flowlet switching, it would simply, assuming that there's a big enough gap, it would break up those elephant flows over equal cost multipath. With flow prioritization, it does something different. It essentially said, and it kind of makes sense when you think about it, why they're mutually exclusive. So the idea is that it takes this real traffic, which is typically a mixture of large elephant flows and smaller mice flows, and it detects these basically flowlets of elephant flows, and it prioritizes the smaller mice flows first to egress. So basically what happens here is it's kind of almost like priority queuing, but without the strict feature, okay? We still have that idea, right, in QoS, but this basically says that we're going to egress our mice flows before we egress our elephant flows. So that's kind of what this does. It's great. It works really well. I think the TCP flowlet switching works better, but you can try both under load and take your pick and learn what you like the best.